Good morning, student. Today I am going to discuss the more realistic and widely used model of electrical double layer, and that is Stern double layer model. In my previous lectures, I had discussed about the two important models. One, as you are all aware of this model, that is called Helmholtz and Perrin model, which is supposed to be the starting model, and there was some problem. So the second model was developed by Gauss and Chapman, and of course there are certain limitations and difficulties. There is a mismatch in experimental observation. So a great scientist, Nobel laureate in physics, German scientist, Professor Stern, developed this model, and which is also 100 years old model. And if you see the literature, you will find large number of modifications, but I will only concentrate on your syllabi of M.Sc. second semester electrochemistry. So therefore, today I will discuss only on the Stern model. As you know that before going into details derivation of that Stern model, I must tell you the genesis of this Stern model. Why this widely accepted and advanced model is required, or you can say that what are the limitations of that Gauss and Chapman model. And as you know that I have already discussed in electrified interfaces, when we study all these models, one of the most important parameter is that differential capacity, or you can call it differential capacitance, and which is very simple, that you know that change in charge with respect to the applied potential. And the first model is that Helmholtz model, where the differential capacitance is dq divided by dv. It is a potential, applied potential, and it is a dielectric constant, and the distance between these two parallel plates is just like a condenser plate if it is a positively charged, and the distance is d. And according to that model, there is no change in capacitance. Then, but this is not true. Then the second model, and of course with the help of Helmholtz model, we have developed the electrocapillary curves and others. I will not discuss this. Now again we see the second model, which is derived by Gauss and Chapman, and here is also same thing, but we have already seen that there is a decrease in this potential. And if we plot a graph between the differential capacitance and the potential, actually we should get a inverted parabola, but that is not obtained. And of course, I have already derived very categorically the Gauss and Chapman layer. If you see my previous lecture, that derivation is very big, but if you compare the derivation of Gauss and Chapman and the Stern derivation is very simple. But again, that problem is there. And if you ask me, sir, what is the actual definition of the differential capacitance? So I must tell you the incremental change in stored charge, total diffuse charge with respect to that potential, and we'll get this cos a function with derivation. So this model is not very realistic model. What I am talking about, this Gauss and Chapman model. And during the derivation of that Gauss and Chapman model, we assume that these ions are just like a point charge. That is not the true, because you know that ions have different sizes, ionic radius and other things. Second problem was that they will not consider the ion-ion interaction, because if the concentration will be very high, there are some low concentration as well as the high concentration. So then we must consider that interaction. And that model could not explain the assumption of the point charge. And another important point is that generally when we calculate this differential capacitance, we need the dielectric constant, which is very important. And that time in Perrin model also we assume that that is a constant, but that is not the truth. And ultimately, as I have already told you, the most important failure is the disagreement with the experimental behavior. I'll just show you one of the graph, which is very important graph. And I have taken this graph from the book Modern Electrochemistry by Bockris Reddy, Naldico, second 2A. But actually they have already also taken from this research paper, Journal of Physical Chemistry, 1988, it is published. This graph is there, and they have changed the concentration of this NN dimethylacetamide in sodium sulfate, and this, you know, the mercury and solution and interface. And basically what happened that if I plot a graph between, this is differential capacitance and this is, you know, that electrode potential. So what happened if we follow that cos function, which I have already shown you. Yes, this final equation. This is actually differential capacitance. So there must be a inverted parabola like that. And you see that there are three different concentrations. And you see that the behavior is different. It is a hypothetical type of things. There is no matching between these. And because that is very important, differential capacitance with respect to electrode potential, and there is a point that is called the PZ, point of zero charge, which is very important, where we will get the maximum capacitance. So the conclusion was that the experimental differential capacitance potential curves do not exhibit the inverted parabolic shape predicted by the Gauss and Chapman diffuse layer. What does it mean? Means that if that equation follows that Gauss-Chapman model, so we must get whatever the concentration, whatever the electrolyte, univalent or unidivalent electrolyte, that must be a inverted parabola. But it also depends upon the concentration. I'll show you, because they have taken the three concentrations. So it is only true where the concentration is very, very low, and at potential close to the point of zero charge, the experimental curve resembles the Gauss-Chapman behavior, because there is a very important significance of that point of no charge, because it depends the actual scattering of the ions, whether there is a change in decrease in the potential. That is the important point, because minimum capacitance occurs at the point of zero charge. The diffuse layer is least compressed, but as we moving away from that point of zero charge, the diffuse layer becomes more compressed and differential capacitance increases. So these behavior could not explain by that Gauss and Chapman. So therefore, you can start from here. If there is a problem, that write the demerits of that Gauss and Chapman layer and how that Stern modified that theory. So you can start with that in 1924, he published a paper. I will show you that paper, of course, in the German language. So he actually rectified all the difficulties of Gauss and Chapman layer and proposed this new theory. Now, theory is very simple, because if you understand the Helmholtz model or compact layer of the Helmholtz model and diffuse layer of that Gauss and Chapman model, if you combine these two things, you will get the final derivation of the Stern model. So it is very easy. That means the total, if I want to calculate the differential capacitance of that whole system, it is 1 by C is equal to 1 by H capacitance of due to Helmholtz, capacitance due to Gauss and Chapman. Everywhere there is a decrease in that potential. That is to be calculated. So he combined Helmholtz compact layer, ions in contact with the electrode, because that very near to that they stuck on that electrode due to adsorption or whatever it is. And after that, there is a scattering of that movement of the ions due to thermal and electrical motion and other things. So we have to combine this Helmholtz model as well as the Gauss and Chapman model. So derivation is very simple as compared to Gauss and Chapman model. So let us start this thing. I have already told you that this is the original research paper published in 1924, and I have taken from the online library of the Wiley. It is available on the internet, and of course it is an advanced, more realistic and widely accepted. I am not saying that this is the ultimate model. There are other models, the Bockris and Devenathan model, Graham model, but as per your prospectus, today I will concentrate only on that Stern model. So, in my first lecture related to the electrified interface, I have already discussed three models separately, but here I will concentrate only on the Stern model. So, as I told you, that he combined the Helmholtz layer and Gauss and Chapman layer. So, if I take this thing is a positively charged surface metal, like suppose positively charged, and it is not very close to that electrode, the counter ion, like this is negatively charged, and the distance it is a compact layer, just like a parallel capacitor, you see, and the distance between these two is d. Suppose I am taking d, you can take a also, and then there is some scattering of the ions due to the thermal movements and other things. So there are some other ions and counter ions in there. Now what is important here, that up to this, if you see very carefully, that there is a sharp decrease in the potential. this red color. There is a sharp decrease in the potential. And again, in this diffuse double layer, that is also decreased gradually. That is called the exponential decrease. So we have to calculate this change in potential due to this perine or Helmholtz layer, and this is the your diffuse layer. You just mix it, and this part is called the outer Helmholtz plane, and this part is called the inner Helmholtz plane. But that part is important. Outer Helmholtz plane. So now I think it is very clear that electrodes, the charges are stuck on this thing. So eliminating the point charge approximation of the diffuse layer theory, ions have a different size. First assumption. Second, that the center of an ion cannot come closer to a distance. Maybe some electrostatic things and other things. And this creates a thin layer between the electrodes and the ions. And of course, this depends upon the low concentration as well as the high concentration. After derive this thing, I will discuss what is the role of low concentration and the role of high concentration of that diffuse layer. That is very important. Now, for just recapitulation, just if you forget the Perrin model or Helmholtz model, so just to remind you that here, if I consider the Helmholtz layer, so this is, you know, that QH is the charge, Q is the charge, total charge of Helmholtz H. Here ions are immobilized, that means fixed, close to the electrode, located at the outer Helmholtz plane, forms a compact layer. Now, in the Gauss-Chapman, where that charges are spread out in the solution from the diffuse layer. So, you know that one is compact layer, then diffuse layer, metal, compact layer, then diffuse layer, then electrolyte solution. You know, this is the system because we prepare a series. So, distance from the electrode. Now, if you ask me, sir, what is the formula of this thing? Because if I want to calculate in the elementary part, I discussed about what is differential capacitance, because that is our target, main target. So here, because it is the combination of the Helmholtz layer as well as the Gauss and Chapman layer, so therefore the total differential capacitance you can call also differential capacity. So that is equal to, you know, that it is QH diffuse charge, whatever the charge, total charges of Helmholtz layer plus total charges of, because that is important and it depends upon the concentration. So Helmholtz and Gauss, if I take now a series as I have already said, one is metal, here is positive, then compact layer, and this is the CH, you know, the capacitance of the Helmholtz layer, then again diffuse layer, Pg, and this is the bulk solution, electrolyte solution. So if I just make a series, so our final result will be, I will explain how we get this 1 divided by C total is equal to 1 divided by CH. So this is the final equation of Stern layer. Very, very simple. So now how we derive it. Now again, as you know that for the derivation, I have referred large number of books, large number of research papers. Again, my intention is that student friendly derivation And let me frankly, I must tell you that for complete derivation, I have referred this very, very famous book, Modern Electrochemistry, second part, Fundamentals and Electronics, second edition by Bockris, Reddy and Gamboa Aldico. And for also derivation, I have also taken this book, Textbook of Physical Chemistry by Morgan. But some fundamental information, because it is a very, very old book, An Introduction to Electrochemistry by Samuel Glaston. The last chapter that he has also discussed something about this turn, the beta potential, electrophoresis, because these are all interrelated. So I have also referred this book, and as you know that my most favorite book in physical chemistry, Atkins Physical Chemistry. So there is a chapter, electrical double layer, and very elementary they have discussed the Stern layer. So I must acknowledge this book. In addition to that, I have referred some research papers and internet materials, etc. So derivation is very simple, because if you see this graph, so if I take just for a explanation, so it is a metal, then compact layer, then this is scattered part. So there is a potential drop, and we can also calculate the beta potential is also. I will not explain this thing. So this potential drop is important. And why this potential drop occurs? Due to the separation of the ions. Separation of the ions. Okay. Then there are some electrostatic force and other things. So the Stern layer behaves like a capacitor. You know the definition of this capacitor, store the energy. So using electrostatistics, the surface charge density. I am first talking about that Stern layer. It's a very old definition, but you must know this thing, because the surface charge density is equal to potential at zero distance, starting point, and this outer Helmholtz layer, the distance is d, whatever the change in this thing, so that's the difference between this. So that is actually surface charge density, because we have to calculate that QN, surface charge. And so I can also calculate this dielectric constant is divided by d, and Ch is the Helmholtz capacitance. So surface charge density is equal to Q is equal to that, this part charge and radius. So this indicates the linear potential drop across the. So don't get confused. It is a recapitulation. You have already studied this thing, Helmholtz model. Just I am repeating the same thing. Similarly, so this indicates this drop. Okay. Now this exponential drop, and I have taken from my old previous YouTube video, where now this exponential that can be calculated with the help of this. This sign is 0, again at distance it becomes 0, and this is a thickness of the ionic atmosphere, and Kx like that. So psi decrease exponential with the distance x. So you can got it. So now I just mix these two things, the last derivation. So when I discuss about the potential variation is linear in the Stern layer and exponential in diffuse layer. So graphically you know that mu 0, mu d, ultimately it is 0. That is the thing. Now first derivation. Because derivation is very simple, nothing to be worried. First point is that how do I calculate the two potential drops? One is for Helmholtz, another is for the Gauss and Chapman. Why there is a potential drop? I have already discussed. That is the separation of the charge. How I calculate the total potential difference across the entire electrical double layer. So that is actually why, because you know that first is metal, then the compact layer, then is diffuse layer, and then is the bulk. You follow my point? There are four parts. So there is a potential drop between metal to that compact layer, and then Helmholtz layer to bulk. So the total potential difference phi of M, that is due to the metal. So you see here, and phi of B, bulk solution or electrolyte. You can write small b, you can write BULK, you can write B, whatever you want to write. So the total potential difference across the entire electrical double layer. So phi of M, phi of B, this M and for one case, actually total, if I want to calculate total thing, so there are two potential drops. One is Helmholtz, another is the Gauss and Chapman. How do I calculate the Helmholtz? From metal to Helmholtz, difference between the metal to Helmholtz. How do I calculate the Chapman? Helmholtz to bulk. You follow my point? So, you see. So, this is metal to Helmholtz, one case, plus total change. Helmholtz to bulk. And this, you know that it is the inner potential of the metal and Helmholtz, and it is the inner potential of the bulk of the solution. So only one line derivation is. Now we have to differentiate this equation. So what is our final equation? This is our final equation. Now we have to differentiate it, because ultimately you have to calculate the total charge density of Helmholtz layer and the Gauss and Chapman layer. So what I will do? Now the separation of charges and potential regions produce a separation of differential capacitance. Due to this separation of charge, so there is a change in differential capacitance. So how do I calculate that differential capacitance? So this is our equation. Total inner potential changes. So if I differentiate it, that means with respect to charge on the metal, that is important. With respect to charge. This is Q is charge metal. So there are two Q of H and Q of G, Gauss and Chapman. If I differentiate it, it is very simple. dy pi m, this is first. Second, third, so there are three parts. Differentiate with respect to dq and metal. You follow my point? It's very simple. First is metal to bulk, metal to Helmholtz, Helmholtz to weight. Now out of these three, now the denominator part of this last part, again it is an assumption that Helmholtz to bulk, it is the diffuse part, you know. There are two parts, one is compact layer, another is the diffuse part, diffuse double layer, where there is a scattering of the ions, movement of the ions. So if I just consider this dqm is replaced by DQD or diffuse layer. So only one line derivation. First you write this equation, differentiate it with respect to charge on the metal, and then replace this thing. You will get the final equation. So these are equations. So what I am telling that this part must be changed because the total charge on the electrode is equal to the total diffuse charge. Because if I take a metal here, is plus, 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 then this, and then there is a scattering, scattering, scattering. Some hydration is also, I have not considered here hydration other things. Some positive charge is also there. So if I want to calculate, so it is depends upon the total diffuse charge. So therefore, the third part I have written here in place of charge of the metal, I replaced the total diffuse charge. And I have taken this derivation, as I have already confessed, from the book of Bockris and Reddy. They are just following that. Maybe some notation may be changed. So now you can ask me, you know that the capacitance C is equal to, generally what we calculate, charge divided by potential. So it is numerator, it is denominator. So here is also like that, the change in potential, surface potential with respect to QD here. So that means it is reverse, because that means what I can write, 1 by C is equal to V, whatever the potential change is equal to dP, whatever. You follow my point or not? It's a very simple derivation. So therefore, I just replace this. So this will be 1 divided by total. You see. Then 1 divided, this is for metal to Helmholtz compact layer. So 1 by reverse 1 by CH. So you can solve it, like you can also solve it. 1 C by total is equal to CH, CG, and CG plus CH, or CG CH divided by CH. So C is the total capacity of the interface. So it is very simple derivation. Now lastly, I will discuss the importance of this work. So again, I just repeat, it is very simple. I will not repeat this thing. You have to write first the total, entire electrical total potential difference, and because there are 4-part metal, Helmholtz compact layer, then diffuse layer, and then electrolyte solution. So just this 2 part, differentiate it with respect to charge on the metal, and then just you substitute the value of total C, you will get the equation. So the conclusion is that, and you have already, you can also tell me that what is the conclusion, that the total of differential capacitance can calculate by 1 by CH and mix of this thing. So the electrified interface has a total differential capacity that is given by Helmholtz and Gauss-Chapman capacity in series, and it is the clear-cut understanding of electrified double layer region. And if you read carefully the Gauss and Chapman layer, you can understand the movement of the ions, they are obedience of the Poisson and Boltzmann equation. So it is a clear-cut understanding of the electrified. Now it is very clear how we can calculate the total differential capacitance. Second, both the Helmholtz and Gauss-Chapman regions store ions are located consecutively away from that electrode surface and together account for the total potential difference across the electrode-electrolyte interface. Because they have their own characteristics. Compact layer as Gauss-Chapman layer. But what is important is that you must consider this thing, because when you see that Gauss-Chapman, take a plot between the differential capacitance and potential, there is a mismatch. So if the concentration is very high, at higher concentration, so 1 by Cg is very less than 1 by Ca. It is less compressed. So whatever we are getting, that is because now that high concentration, low concentration problem of Gauss and Chapman layer can be solved, can be explained with the help of this thing. 1 by Cg is less than 1 by Ch, so C is equal to Ca. But because at low concentration, this system is right. At low concentration, 1 by Cg is greater than Ca. So whatever we are getting, the total capacitance due to the diffuse layer. So now you can understand this. Now applications, you will be happy to know that, because nowadays people are working for colloids, interface science, corrosion, nanomaterials, so many things. Supercapacitor and battery, fuel cell. Everywhere it provides a realistic model of the charge distribution near the charge surface, and it can also describe the electrode-electrolyte interface in the electrochemical cell. And very useful in electrocatalysis, which is also in your course. Then it will also useful in very colloids and interface science, corrosion, fuel cells, I have already discussed, battery, and double layer capacitance in the supercapacitors and the battery, and many electrokinetic processes like electroosmosis, electrophoresis, streaming potential. You can use the Stern model. And I think you might have heard, I will not discuss today the impedance spectroscopy, electrochemical impedance spectroscopy, very important topic, very important subject. So in electrochemical impedance spectroscopy, the double layer behaves like a capacitor and influences the impedance response of the system. And of course, today I will not discuss about the zeta potential and other things. So the analysis of the zeta potential and other electrophoresis can be solved with that model. So, and if you ask me, sir, what is the next or what further development in this area? So you know that science is a continuous process, and this is, as I told in my previous part, that is 100 years old, more than 100 years old theory. But in 1947, Professor D.C. Graham modified this Stern layer, and he published a very good article in, you know, that a very famous journal, that is the Chemical Review of American Chemical Society, and the title is The Electrical Double Layer and the Theory of the Electrocatalysis. Because Stern or Gauss and Chapman and Helmholtz, they proposed this theory, but now people are using these theories for the applications in electrocatalysis and electrochemistry. So, but this is not your course, so don't worry about this Graham modification, because they consider the inner Helmholtz plane as well as the outer Helmholtz plane. Similarly, you know that I have already referred that book, J. Bockris and Devnathan, very good electrochemist, and Muller proposed the BDM model, Bockris, Devnathan and Muller model, and they also published the Royal Society publishing proceedings on the structure of the charge interface. As a M.Sc student, because you know that we we are giving more emphasis on the research oriented teaching. So therefore, I am just using the conclusion as well as the applications. Whenever you do study any model, you must know that why we are studying such type of models. So I think in this semester, this session, this is my last lecture from the electrochemistry. Very hot summer. Today is, I think, 4th of June, and you are all giving the examination. So in the next semester, I will complete the remaining part of the semiconductor interfaces of this electrochemistry and other things. And really, I am grateful to the Pandit Ravi Shankar Shukla University lecture capturing facility of mathematics departments, and I am preparing around more than 100 video lectures for the students for the Ravi Shankar Shukla University as well as some affiliated colleges. They can refer my lectures, and I am also thankful to Professor Balwant Singh Thakur, who is the head of the department of mathematics, for providing me all the facilities. Another associate professor, Dr. Dipti Thakur of the mathematics department, a young faculty member, Dr. Indra Kumar of this mathematics department, and not but the least, Mr. Abhishek Katendra, my research scholar, for helping me in preparing some graphs and some calculation and formula. So thank you very much.